Good morning, dear friends, students. Myself, Dr. Lingaraju, Government First Aid Degree College, Tumkur. So, today we will discuss diffraction pattern. The diffraction comes in a BSc 4 semesters with us in physics subject, Tumkur University. In the diffraction main chapter, so today we will discuss 3 important points, that is the diffraction definitions, Fresnel half period zone for a plate. So we'll discuss these 2 points. Myself, Dr. Lingaraju, and also my associate, Assistant Professor Pankaja KN, is prepared this PPT and also a notes. So here we know diffraction. Diffraction we studied in 10th standard and also in PUC level also. Diffraction, interference, polarization. So these 3 light effects we are already discussed. In the study of geometrical optics, light traveling in a non-homogeneous medium is assumed to follow a straight line path. That is also we can as a rectilinear propagation of light. According to this, a shadow cast by an object illuminated by a point source of light would have sharp edge. However, the shadow of an object cast by a point source is not sharp. Fringes appear around the edge of the shadow. This is due to the bending of light around the edge of the barrier and is referred to as diffractions. That is we called as diffractions. The definition of diffraction is, if the light will be enters from one medium to another medium, at the time the light will be gets bent. So that one is called as, through a definition we are about to study. The phenomena of bending of light around the edges of obstacles or narrow slits, or hence its encroachment into the region of geometrical shadows, is called diffractions. So here, how we are going to define the bending of light? Bending is a natural property of any wave and is a sure test for a wave. Waves also have a property to spread out. The extent of diffraction depends on wavelength. The longer the wavelength, more being the bending. The phenomenon of diffraction is different from refraction. Refraction is the bending of light as it passes from one medium to the another medium, while diffraction is bending of light when it passes an obstacles or barriers. Obstacles or barriers. So this diffraction of bending of light is passes from one medium to the another medium. So to observing this diffraction, the width of the obstacle should be comparable. That is also very important. The width of the obstacle should be comparable to the wavelength of the wave used. For this reason, it is easy to observe. Diffraction of sound, while it is not easy to observe diffraction of light, since the wavelength of light is very small. That is the phenomenon of a diffractions. Knowing that, just here we discussed wavefront. So wavefront is defined as the locus of all the points of a medium. So focus of all the points of medium which vibrates in a same phase at a given instant of time. Depend on the shape of the source of light, the three types of wavefronts it is going to form. Three types of wavefront it is going to form. Yavyavo plane wavefront, spherical wavefront, cylindrical wavefront. Let us know about the details of these different kinds of a wavefront. So first, plane wavefront. See the diagram, we can observe it. Plane wavefront. So plane wavefront, when a light is coming from a very far off source, very far off source. So this one is very far off source. The wavefronts are planar. The wavefronts are planar. For a plane wavefront, amplitude remains constant. You see, it does not go into varies. The amplitude remains constant. Therefore, intensity remains constant. If amplitude varies, means the intensity is also going to vary. But here there is no any obstructions. There is no disturbance takes place in this particular point of view. So far, we are not going to lose any amount of amplitude. So it means remains constant of intensities. It is wavefront, plane wavefront. Next is spherical wavefront. See, directions of propagations of these light radiations 1, 2, 3, 4, 5, all these things. When a light is emerging from a point source, so from here, emerging from a point source, the wavefronts are spherical in shape. The wavefronts are spherical in shape. In spherical wavefront, amplitude of a light waves A is proportional to 1 by r, and intensity of the light waves is proportional to 1 by r square, square of its intensity, r radius of its intensity. So like that, the light wave will be going to propagation takes place from one place to the other place. Next, third one, cylindrical wavefront. See here, the light will be passes from this side to this side. When the source of light is a linear, see linear, the wavefronts are cylindrical in shape. All the points are equidistant from the source. In this case, amplitude of light waves A is proportional to 1 by square root of r. In this case, the amplitude will be going to vary, that is equal to 1 by square root of r. The intensity of light, that is also inversely proportional to 1 by r. So if r will be decreases, intensity will be increases. R will be increases, intensity will be decreases. Like that, all these things will be going to happen. Of knowing this concept in the diffraction, we are going to discuss eigen principle of secondary wavelets. So secondary wavelets will be arises. How here it is going to changes takes place. So we are going to discuss Huygens principle. Huygens principle of secondary wavelets states that every point on a given wavefront is a secondary wavelet. Huygens principle of secondary wavelets states that every point of a given wavefront in incidental diffraction, so secondary wavefronts will be releases. That is nothing but a disturbance. Disturbance ಆಯಿತು ಅಂದರೆ secondary wavelengths release ಆಯಿತು. So further, the disturbance originating from the secondary source. 1 minute. So after disturbing, how it is happens? Further, the disturbance originating from a secondary source scattering in all directions in the way when originated from the primary source. So that is the causes of a secondary wavelets. After knowing this one, what are the principles for further highlights of the following things? That is secondary wavelets. So secondary sources makes their own wavelets, and these waves are similar to that of a primary source. Similar to that of a primary source. At the instant, a common tangent drawn on a wavelet. Common tangent drawn on a wavelet in the forward directions point to the new wavefront. The spherical wave, how and what point the secondary wavelets are coming. So that is the point here we are going to understand. First one is, at the instant, a common tangent drawn on the wavelets in the forward directions point to the new wavefront. The spherical wavelets together form a wavelet. In conclusion, Huygens principle is the comprehensive method of analysis that we can use to understand the problems of the propagation both in diffraction and reflections. After knowing this one, now here we come to the Huygens principle. How Huygens principle takes place. So I'll discuss. Here you see the diagram. A1, A0, A2. See. So now let us discuss. According to Huygens principle, every point on a given wavefront, can be regarded as a fresh source of a new disturbance, and send out its own spherical wavelets called secondary wavelets. These secondary wavelets spread out in all the directions. You see, in all the directions, 1, 2, 3, 4, 5, 6, like that. Wavelets spread out in all the direction with the velocity of the wave. A surface touches these secondary wavelets tangentially. You see, the surface touches these secondary wavelets tangentially. So, in the forward direction at the instant delta t. So, it gives the position of the shape of a new wavefront at the instant. This is called secondary wavelets. As discussed in the introduction, Huygens principle of secondary wavelets could explain many optical phenomenon like reflection, refraction, interference and diffractions, but it could not be explained wavefront for secondary wavelets are formed in the forward directions and not in the backward directions. That is the one thing. So now, after knowing the Huygens principle, we'll discuss the types of diffractions. So diffraction can be classified into two types, namely Fresnel's diffraction, Fraunhofer's diffractions. Now we come to the first one, Fresnel's diffractions. ಇದೇನು ಹೇಳುತ್ತೆ Fresnel diffraction? Fresnel's diffraction phenomenon where either of an electron source and an observation point, are both of them located at a finite distance from the object. Thus, the incident wave and excited wave cannot be regarded as a plane wave. That is Fresnel's diffraction. A diffraction phenomena where either an electron source or an observation point or both of them located at a finite distance from the object. Thus, the incident wave or exit wave cannot be regarded as a plane wave. So that is the concept of Fresnel's. Fraunhofer. In the type of diffraction that occurs in the limit of small Fresnel number, Fraunhofer diffraction, the diffraction pattern is independent of the distance of the screen. Independent of the distance of the screen. Depend only on the angles of the screen from the aperture. From the aperture. That is we call as Fraunhofer's diffractions. Knowing this one, so we'll discuss the illustrations of a diffractions. The illustrations. A luminous border is observed surrounding the profile of a mountain just before the sunrise. Behind it, this is due to diffraction. Just we can observe at the morning, a luminous border is observed at the surrounding of the profile of a mountain just before the sunrise behind this. This is due to a diffraction of light. Second one, luminous strikes a light seen when a strong source of light is observed with half closed eyes. This is due to diffraction. Second. Third one is colored bands observed when a distant source of strong light is seen through a fine piece of cloth. The holes between the fibers acting as very narrow slit of width comparable to the wavelength of light. So that is also one of the illustration, the diffractions. So and also alternate bright and dark fringes. Or bright bands are seen when we look the straight light between a two fingers pinched together suitably. That is also a diffraction illustration. The colored pattern is seen on spider web. If the light will be focused to spider web, so colored pattern we can observe it. That is also due to a diffraction illustration. The spreading of light when it passes through a small hole in a vacuum object. So that is also a diffractions. After knowing that, now we will come to the Fresnel's half period zone for a plane wave. Fresnel's half period zone for a plane wave. Here we see the diagram we will discuss. A, B, C, D. That is one kind of a plane wavefront of a monochromatic light of wavelength lambda. A, B, C, D is the plane wavefront of a monochromatic light of a wavelength lambda. The wavefront is perpendicular to the plane of the paper. You see, the wavefront is perpendicular to the plane of the paper. Okay. Let P is the point at a distance B from the wavefront at which intensity due to the wave is to be calculated. How much intensity is there here in this region? OP is perpendicular to the wavefront. OP is perpendicular to the wavefront. To calculate the resultant intensity at P. Due to the entire wavefronts, Fresnel assumed the wavefront to be divided into number of concentric half periodic zones. 1, 2, 3, 4, 5, 6, like that. Half periodic zones called Fresnel's half period zones. O is the pole of a wavefront. With P as a center, width B plus lambda by 2, B plus 2 lambda by 2. So P as centers. So this radiation is B plus lambda by 2. This one is M1, M2, M3, like that. M2 is B plus 2 lambda by 2, then B plus N minus 1 of lambda by 2, b plus n lambda. So like that here we are going to find out a series of concentric spheres. Concentric spheres are drawn in the wavefront. These spheres intersect the wavefront in concentric spherical holes or concentric spherical circles. O is the entire of OM1, OM2, OM3 of radii. So knowing this, the secondary waves from any two consecutive zone reaches to the P with a path difference of lambda by 2 or the time interval of T by 2. Hence these are called half period zones. Half period zone. The area of the circle of radius OM1 is the first half period. So like that here we are going to define. So next, similarly, the area between the circle of radii OM2 or OM3 are the second half period zone and so on. Third half period zone, like that here we are going to calculate. The angular area between nth and n minus 1 circle is nth half period zones. Like that here we are going to this one, nth half period zones. So knowing this concept, so now here we are going to calculate the radius in a half period zone. Now here we come to the first one, OM1. OM1 is equal to, based on this formula, is equal to square root of m1p square minus op square. m1p square minus op square. So what is the radius? We are going to calculate this value. OM1 is equal to m1p square means what is the value? So b plus lambda by 2 whole square minus op square means the distance is b square. So from the figure 1 we can easily write, simplify this, OM1 is equal to square root of b lambda. Square root of b lambda. So neglecting lambda square by 4 as b is greater than lambda. So this is the radius of the first half period zones. Like that here we are going to calculate half period zone. So like that one more other, that is OM2. OM2 square root of m2p square minus op2. So like that here also we are going to get, here we are getting 2 extra. So like that we are going to calculate. Similarly for OMN, half period zone. So instead of 2 here we are getting n values. This shows that the radii of the half period zone are proportional to the square root of the natural numbers. This is so that radii of the half period zone are proportional to the square root of the natural numbers. So next, after knowing this concept, to find the area of the half period zone. That is very simple. The area of the half period zone is AN is equal to pi of OM square minus pi of OM minus M square. So substituting these values, we get a pi b lambda. So it is independent of the regions of n of radii. This shows that the area of half period zone period zones is equals. So knowing this, you can write the amplitude of the disturbance at P due to an individual zone is first one directly proportional to the area of the zone. The amplitude of disturbance different. So there is P due to individual zone directly proportional to the area of the zone. Second one is inversely proportional to the distance of the point P from the given zone. Third one is the obliquity factor 1 plus cos theta, where theta is the angle between the normal to the zone and the line joining the zone to the point P. Line joining to the point P. Like that here we are going to calculate the half period zone. So it's about our diffraction pattern, diffraction concepts, and also the types. So I have referred so many different kinds of reference books and also prescribed textbooks. There is a Sundarajan, Subramaniam, and also 3 different college Tumkur University prescribed textbooks. So myself and also Pankaj madam. Thank you dear students.